Swayam Prabha. Digital India. Educated India.
Okay, so I think by now the listeners should be fairly clear as to what sort of how to set up the Lagrange equation for any motion which is holonomic, right? Whether it is standard or whether it is conservative. So now let us now talk about the setup where we have kinematic constraints in the system. How to write down the Lagrange equation of motion for kinematic constraints. So what we are now going to talk is system with moving constraints. System with moving constraints. So we see that let us assume the standard system. If the constraint is fixed. Let us assume the standard system if the constraint is fixed, and let us say that the configuration Ri of a system with moving constraints this time is going to be we'll have to talk about the velocity of each particle in the system. So what we have is the particle velocity, the corresponding particle velocity that we are talking about. Particle velocity is given by Vi is given by partial Ri partial Q1 times Q1 dot plus partial Ri partial Qn times Qn dot, right? So this is my velocity in the generalized coordinates. Plus, well, what we have forgotten is we should not forget there is one more hidden variable in the system, which is the time itself. So dr dt, right? So time is an independent variable which is implicitly hidden. Now what we are now talking about is a system which is non-autonomous, that time explicitly appears. So not only functions, we are dealing with functions of q and q dot, but we are also dealing with functions of t as well. So that is the difference between when we were dealing with holonomic constraints and now dealing with non-holonomic constraints. So then I can now write my kinetic energy this time. So my kinetic energy T of q dot, well, T of q comma q dot comma T is given by summation j from 1 to n, summation k from 1 to n, ajk of q comma t, qj dot qk dot. So this is my kinetic energy, and plus summation bj of q comma t, and this is j from 1 to n, plus c of q comma t. So what I am hypothesizing, what I am claiming is that my kinetic energy this time will be of the most generalized form. It won't just have the first term that was in the holonomic constraint form, but it will have also terms of the form which is the term number 2 and term number 3, which contains time explicitly. And even in the first term, the coefficients will have time implicitly. So then, well, the major implication of this type of a setup where time appears explicitly is that this time energy will not be conserved. Energy is not conserved, not conserved. And then which means that the another implication of this setup is that this time the constraint forces do net work. The constraint forces do net work. The constraint forces do net work, which means that T plus V is not a constant. The total energy of the system is not conserved, or the total energy is not a constant of the system anymore. So now what to do? So what we have to do is to set up again the Lagrange equation with moving constraints. So let us try and do that. So Lagrange equations with moving constraints. So this question now that again we have to ask, that the one that we asked few slides back was, can we have a consequent principle of virtual work for non-holonomic system as well, like we had a principle of virtual work for holonomic system. So this question we are asking is this sum from I1 to n fi of c dot with partial Ri partial Qj equal to 0 true? Is this system true? Then the answer is yes. So we should breathe a sigh of relief that the answer to this question is yes. We certainly can make the constraint, we can find these variables in such a way that the dot product of the constraint forces with these variables are turning out to be 0, and we can have a corresponding principle of virtual work. So which means, and the question is, how come this dot product is 0? The answer lies in the fact that this quantity d partial Ri partial Qj, this is a derivative at constant time. So this is a derivative at constant time. This is a derivative at constant time, which means that because t is an independent variable, right? So that is certainly true. T is an independent variable, and this is a derivative at constant time, partial derivative. So then in that case we can certainly use our same ideas of principle of virtual work where time was not appearing, right? Because here we have fixed time. So time is constant means time is fixed, or time doesn't appear in the calculation. So which means that again the another set of questions we can ask is this sum mi times vi dot partial Ri partial Qj which is also equal to ddt of dt dqj dot minus partial t partial Qj. Is this also true? This question is it also true? Is it still true? And again the answer to this question is yes. This is certainly true, because the extra term that we had, remember when we calculate, the kinetic energy T also has a new variable small t, which is time. But the extra term is not going to contribute anything to this equation. So the answer still is yes, because the extra term which is my dri dt, right? Partial Ri partial t, we will have these extra terms. Why? Because when we do all these derivatives on the right hand side of this Lagrange equation, we will, and use chain rule, we will have these derivatives of the form dri dt. So this in velocity do not contribute anything. Do not contribute anything, right? Why? Because the time is fixed here. So that is what we expect. So, and then finally the third question we need to ask is this quantity summation fi of s dot with partial ri partial qj which is also equal to partial v partial qj. This is for the conservative system. Notice how we are cleverly using the equations for conservative system for a system which is non-conservative. That is the genius part of this Lagrange equation. That the Lagrange equation is general enough that even though the system may not be conservative, you can still use the Lagrange equation of motion. So that is the generality of this setup. And that is the superiority that you get for Lagrange equation versus the Newtonian mechanics. Okay, so the question to the third part is this true? The answer is yes. Because again the partial derivatives are evaluated at constant t. The partial derivatives are evaluated at constant t, and you see that the Lagrange equation this time hold with moving constraint as well. The Lagrange equations hold with moving constraints provided t is an independent variable. T is an independent variable, right? So you see the Newtonian setup completely falters. Why? Because energy is no longer conservative, the total energy is no longer constant, but the Lagrange equation is perfect. The Lagrange equation works even for non-conservative system as long as our time is an independent variable of the system. And we are good to go. We don't have to rederive the Lagrange equation because the Lagrange equation holds for the non-holonomic system as well. That is the best part of the Lagrange setup. Okay, so then let us now look at another example for this non-holonomic setup. So the example that I have is the particle which is oscillating, the pendulum which is oscillating. So this is oscillating pendulum. Okay, so what we have to do is we have to find the Lagrange equation for the driven pendulum. The Lagrange equation for the driven pendulum when the displacement function z of t is given by z naught cos pt, right? Let me draw the diagram and it will be fairly clear. So we have the point of support is O, and from here we have a pendulum which is not your regular pendulum. Why? Because the pendulum doesn't have a fixed point of support. The pendulum is moving up and down z of t given by the vertical distance z of t, and we see that this is going to be this is the vertical distance downward, and now the pendulum is attached to some support which is moving up and down. So now here is the bob of the pendulum, which is, let's say, particle p, and the vertical velocity is z dot of t, and we see that this is theta. And let us now, so what have we got here? So the coordinate frame is that the horizontal axis is I hat and the vertical axis is k hat, right? The z axis. Okay, so then, well, again, the listeners should not be confused. Sometimes I call the vertical axis as y hat, sometimes I call the vertical axis as j hat, or sometimes I use the variable z for the vertical axis. But let us now, most important is we need to fix a coordinate frame, and with respect to, and also the direction, the perpendicular directions along which we have to write our equations of motion. So that is something which we need to be clear about. So here the directions of motions are along I hat and k hat. So now we can see that while this pendulum has, this moving pendulum is acted upon by a weight of mass mg, but it is also rotating about this moving support. So let us say this rotational velocity, this tangential velocity of this rotation will be a theta dot. So what we see is, we can now write the kinetic energy of the system. The kinetic energy, well, before we move ahead, I am sure to all the listeners that this is a case of a non-holonomic system. Why? Because the pendulum is not fixed to a point which is fixed or a fixed support. The pendulum is that of the case of a driven pendulum, which means that there is some sort of an external force acting on the pendulum with which the pendulum is moving downward, and its vertical distance is z of t, right? So which means that due to external forces, the energy of the system is not conserved. But fortunately, we can still write the Lagrange equations. So for that, let us write down the kinetic energy of the system. The kinetic energy is T is half m a square theta dot square plus z dot square minus 2 a theta dot z dot sine theta. And then my potential energy V is minus mg z plus a cos theta. So that is my potential energy. Why? Because the vertical distance is z of t plus the distance which is downward subtended by the pendulum is a cos theta. So I put a minus sign because the distance is below the base, which is 0. The base is the point of fixed support. So now the potential energy is this, and let us now write down the Lagrange equation. So we see that my partial t partial theta dot is going to be m times a square theta dot minus a times z dot sine theta, because z is also a function of time. And we see that partial t partial theta, we can differentiate. We see that this is minus m a theta dot z dot cos theta, and we see that from here my velocity, my potential V is minus mg z plus a cos theta, right? So that is my potential V, which is z plus a cos theta. And well, we can again evaluate. Well, V I have already written. I don't need to write V again, but I need to write the derivative of V with respect to theta. And we see that this is going to be minus mg times z. Well, mg, z is not there. So with respect to theta, this is mg sine theta with a plus sign. So theta is only appearing in the second term of the potential. Okay, so then we can further now assume that z is of this form. Z is z naught cos pt. So we can plug everything here. We can plug it here. And now we are ready to write down the Lagrangian or the Lagrange equation of motion. That the Lagrange equation comes out to be, let me call this as LE, is d dt of ma. Well, we have to substitute this quantity inside d dt, which is dt d theta dot. So this is ma times a theta dot minus z dot sine theta and then plus ma z dot theta dot cos theta. So that is the second quantity here, dt d theta with a minus sign. So that will become plus sign. and then on the right hand side I have to worry about dv d theta, which is mg sine theta. So that is my net force. So I am now using the term of the potential in exchange of the right hand side of the Lagrange equation. So that is how we write down the Lagrange equation. I think we have to use minus dv d theta. So we have to put a minus sign here. So that is my Lagrange equation with respect to variable theta. Now, do we have any other Lagrange equation? It turns out that my only Lagrange equation is only this which I have listed, and t being an independent variable, t is not going to appear as a generalized coordinate. So t is not a generalized coordinate here. That is the point. The only generalized coordinate that we are worried about here is theta. And we have written down the Lagrange equation of motion, and we can simplify this equation. Let me call this as, we have already termed this as equation number 1, and let me rewrite this equation 1. So 1 becomes, I am going to simplify everything, divide throughout by the mass, and we get that this is theta double dot omega square plus z naught p square by a cos pt, and this is going to be times sine theta, which is equal to 0, and where my omega, capital Omega, is given by square root g over a. We plug everything, and interestingly we see that this is an equation of simple harmonic motion. Of course non-linear, because we have a sine theta appearing here, but interestingly, if we choose certain fixed values of these parameters like z naught, p and a, we can even produce chaotic motion. That is the beauty about simple harmonic motion. So people who want to visualize the dynamics of these equations can go home and try plotting the solution of this equation 1 for these parameters p by omega equal to 1.9, z naught by a equal to 0.2, and theta naught being the initial angle being 0.1 radian. And we go home and check that this is certainly the case of a chaotic motion. So a simple harmonic motion producing a chaotic motion. So with that, I really wrap up our discussion here of the first module, and in the second module I am going to talk about a concept of Lagrangian from the Lagrange equation, and later on in our other modules we will talk about a concept of the so-called Hamiltonian, and how these Lagrangian and Hamiltonian are related with a very well-known theorem known as the Liouville's theorem. Thank you so far for listening.